Hello, math fans. This is going to mostly finish my discussion of cribbage. We may do more if I come up with more ideas. But this is the main question that I played. As I mentioned in previous videos, I used to play cribbage with my son every morning. This video is mostly dedicated to my Uncle Rick and Aunt Sharon and Cousin Gail, who also love cribbage, and so that pushed this to the top of my list to want to do. This particular video is a much more mathematical, and I wanted to talk. We were talking about the issue of how we count the number of ways we can get 15, and this made me think of something from long ago that I really enjoyed. Was we can actually use generating functions and power series to do such things. Now, what do I mean by that? So if you do something like 1 plus x squared plus x to the third, and you multiply that times 1 plus x squared plus x to the third, to multiply that, it's a bit tedious. You do every possible combination. This times that, this times this times this. But I just need to talk about this a little bit. But certain things will happen. So like, for example, when you multiply 1, you're going to get 1 plus x squared plus x to the third. When you multiply by x, you're going to get x. I'm going to line them up in a funny way. X times 1 is x, and then you're going to get x squared plus x to the third plus x to the fourth. When you multiply by x squared, you're going to get x squared plus x to the third, plus x to the fourth, plus x to the fifth. And really, when you're putting two things together, like when you multiply this times this, you are actually adding 2 plus 2 makes 4. And that's how this comes into play. This gives a really unusual and powerful way to add things together. So if you multiply by x to the third, it's a surprisingly powerful way to count things. Now, if you're having to do this, it's no better, but you can then combine like terms. So 1 plus 2x plus 3x squared plus 4x to the third plus 3x to the fourth plus 2x squared plus x to the sixth. And the point of me doing that example was to talk about these numbers. So what does 3 represent? 3 represents all the different ways that we were able to get 2 where we were allowed to use the numbers 0, 1, 2, or 3. We're actually using the exponents. It's an incredibly clever idea. So if you think about the number 2, how many ways can you write it if you're allowed to use two numbers added together, and they can either be 0, 1, 2, or 3? So you could have 0 plus 2, you could have 1 plus 1, or you could have 2 plus 0. 3 ways. How many ways can you get 3? You can have 0 plus 3. You can have 1 plus 2. You can have 2 plus 1. And you can have 3 plus 0, 4 ways. When this becomes more interesting is what if you want to multiply more things? Not just 1, 2, 3, 4. Maybe you want to allow 3 spots. If you wanted to allow 3 spots, you could multiply by it again. 1 plus x squared plus x to the third. What if you didn't want to allow this one to have a 3 or a 2, let's say? You could erase that one. What if you wanted 1 to just be the even numbers? You can do that. So yes, the expansion will be bad, but this actually leads very nicely to things that otherwise would be hard to do formally. And there's even more. And then I'll apply this to the cribbage problem. So if you then took everything, x to the 1, x to the 2, x to the 3, x to the 4, forever, that's called a power series. And it actually has a representation. It's equivalent to 1 over 1 minus x. That's something we talk about when we talk about Taylor series in Math 126, if you're one of my students. We don't talk about this, but to me it's one of the most interesting examples, applications of what we do. For example, if you plug in this only makes sense if your number is between -1 and 1, strictly between. If you plug in a half here, it turns out that 1 plus a half plus a fourth plus an eighth plus a 16th adds up to 2, which is equivalent to this. But an interesting thing here is this can encode every possible way. So if you just take this, for instance, this is also 1 over 1 minus x, and you expand this out, it will give every possible way to add up to some number where you're allowed to use the positive numbers. And we can actually get a particular coefficient, and I'll show you this. Let me pull up a little calculator. Because this all involves calculus, there's actually many ways to get this. So let's say we wanted to know the coefficient of x to the third of this. There are fast ways to do such a thing. The coefficient of x to the third of the power series 4. Let's see if that. I have to figure out the right way to type it in. Oh man. All right, I'm going to do it a different way. The third derivative of this. So third derivative of this, the reason that comes into play is if you actually could expand this out, and it was something plus something times x plus something times x squared plus something times x to the third, and we would like to know this number. And again, this is much more mathematical heavy than some of my other videos, but we would like to know the number of ways to get 3. And we know the answer. It's going to be 0 plus 1. 0 plus 3, 1 plus 2, 2 plus 1, 3 plus 0. There are 4 ways. It turns out that the number in front of there is always equal to what happens if you took 3 derivatives. Now, if you don't know anything about derivatives, the derivative of this is 3x squared. The derivative of that is 3 times 2x. And the derivative is 6. So if you take 3 derivatives, you're going to get 6 times the correct answer. So it turns out you have to divide by 6. So if you take the number here that we got, 24, and divide by 6, you get this number. I know it's a big thing I'm making, but it's that number. Okay, so what is this leading to? And it turns out you don't just divide by 6, you divide by 3 factorial. Everything 3 times 2 times 1. Well, the point of this is now we can ask all sorts of questions in a symbolic way and use what's known about calculus to compute it. For example, how many ways can you get the number, I don't know, let's make it 7, but we are only going to allow this one, we'll say this one can't be 0. So we'll say we want it to be, we're only going to allow the numbers 1, 2, 3, 4, 5, 6, and beyond. And here we're only going to allow the even numbers, 2, 4, 6, 8, 10. So how do we do such a thing? Well, the general way is you would like a tailored polynomial. You'd like this thing that has all the numbers, and then you'd like one that only has the even numbers. And it turns out there's an easy way to do that, which is this. Basically replace all these with x squared. And now you would want the 7th derivative of this, and then you plug in, then you divide by 7 factorial. I know it's a lot of math speak. This is much more for my math people, but it's so unusual. This use of Taylor series this way. So let's do this. I've never done this. We're going to do the 7th derivative of 1, and I hadn't thought about this in a long time. 1 over 1 minus x to the second. Oh, it gave me a really bad thing. I need to say evaluated at 0, at x equals 0. Assuming evaluated is a weird word. Oh, and then I need to divide by 7 factorial. Divided by 7 factorial. 4. This comes out to be 4. But it's a problem that otherwise would be hard to sort of track in a general way and gives us a formulaic way to get it. Let's see if we can find those 4 solutions. So you can't have 0 now because we are allowing 0 over here. So you could have 7 plus 0. What else could you have? This has to be an even number. So you could have 2 plus 5. You could have 4 plus 3. And you could have 6 plus 1. That's it. That's the only way that you could have an even number in the second spot. But what's interesting is how you can tweak these things the way you want. Okay, with that background, let's step into the cribbage problem. This is what I remember. I suddenly had this little memory of this as I've been thinking about this problem today. And I was like, can I make this work? Can I come up with polynomials that can help me count this? So I just thought that was interesting unto itself. It might be interesting to some of my students that are going to go back into Calculus 2 and maybe have to do stuff with Taylor series, and everyone hates that and thinks it's messy. So what we're trying to do when we're trying to count cribbage is we're trying to get a 15. And part of the challenge is we might use a lot of different numbers to get it. But we do have some restrictions. One possibility is that you could have aces. Aces count as 1. You could have 1 ace. You could have 2 aces. You could have 3 aces. And I had to think about this a lot today to sort of get things to line up. But there are several ways you can get aces. Watch my previous video on that. How many ways can you get 1 ace? Well, you can get that 4 choose 1. It's 4 ways. How many ways can you get 2 aces? There's 6 ways. How many ways? Watch my previous video on that. How many ways can you get 3 aces? There's 4 ways. So think of this as representing the aces, and it includes the number of ways we can get it. So I'm pushing it a little further. I didn't talk about that. So then I'm going to include the 2's, but I'm going to do it by thinking about the power. So 1 plus x squared plus x to the 4th, that would be 2 2's, plus x to the 6th, that would be 3 2's, plus x to the 8th. But there are 4 ways you could have 2 2's. There's 6 ways. There's 4 ways you could have 1 2. There's 6 ways you could have 2 2's, or you could be a ballerina. And there's 4 ways you could do that. So if I expand this out, it will give me all the things I can get by adding aces and 2's in a deck in every possible way I can do it. So for example, if I did this multiplication and did this times this, I would get 1. I would get 4x squared from this times this. And I would get 6x squared from this times this. So in total, I would have 10x squareds. And that means there's 10 different ways that I could get the number 2 if I'm only allowed aces and 2's. So I could have ace plus ace, and there are 6 ways to choose that because there are 6 different ways you could have 2 aces. Or you could have a 2, and there are 4 different ways to do that, and that adds up to 10. This encodes all of that information. Now, we don't care about 2, we care about 15. So I need to expand this and get to x to the 15th and see what number is in front of there. Okay? So let's do it. Okay. And in this case, I'm not taking derivative. I'm just going to, if I take derivatives, it's a little different story. So I just need to know the number in front. So then I went and looked at I was just thinking there for a second, because I still have some unanswered questions. I went and looked through the gentleman the only other place I could find online that had done this. And I looked for examples where they used only aces, twos, and threes. And the number in his list, here were the examples where he only used aces, twos, and threes to get 15. So 4 aces makes 4. 4 fours, that's 8, so 12, and they added 3. And there were 4 ways to do that. And I counted all those up. And then that person's list, I appreciate that person making a list, they had 320 ways. So then what I did is I did the following. I went into Mathematica and I made this. So here's the aces. 4 ways you can have 1 ace. And the reason it's aces is these are going up by 1. 1, 2, 3, 4. And then I did the twos. 2, 4, 6, 8. And this is a higher level, but this just gives you a little taste of some of the surprising things you can do. This isn't actually a series. It's not a power series because it's finite. I guess it is a series. Series usually implies infinite. I'm truncating it. I could add more powers. The reason I didn't go further was because I didn't need to. So I asked for the coefficient of x to the 15 of this thing, and I got 320. And I was like, I'm on to something here. Okay, so then I said, what if I allow 4s as well? So now I'm going to allow 4s. This is this is 8, this is 12. Those are the multiples of 4. Same thing, there's 4 ways you could have 1 4. There's 6 ways you could have 2. What's nice is I could just type it in and I didn't have to list these things out. So I counted those up in this list and I got this. 3,176 ways. And all I had to do was type that in and coded it in a way that I could use calculus and Mathematica to do it. So then ace 1, 2, 3, 5. I know it's getting a lot bigger. Oops, I didn't mean to type that in. That's my final answer. So let's go do that one now. So let's pull this up. Mathematica. It's just surprising. It's very different. So I'd like the coefficient of 1 plus, maybe I have it in here. I do have it here. Let's grab that. I'll put it in here. So this just shows, if it was really important, and this problem's not that important necessarily for anybody, but counting things. Often people talk about the number of ways proteins fold or something. You could see something like that being pretty darn important. And so counting things, counting the possibilities, can be pretty valuable. Let me just type this in. Coefficient of x to the 15th in this thing. So here we go. There's that 320. So now let's include the powers of 4. 1 plus 4 times x to the 4th. There's 4 ways you can get 1 4. There's 6 ways you can get 2 4s. There's 4 ways you can get 3 4s, which makes 12. And there's x to the 16th. Now I don't really need to put x to the 16th if I'm counting 15s, because there's no way an x to the 16th is going to be multiplied to give me an x to the 15th. 3,176. Okay, let's keep going. I meant to copy and paste the next one in, but let's do 1 plus 4 times x to the 5. Now we're at 5. Plus 6 ways you can get 2 x's, which would be 10. And 4 ways you could get 3 x's, which would be 15. Coefficient. 7564. Thing of beauty. So I stopped there. My eyes were tired, and I've already spent too long on this. But I just really enjoy working with these polynomials. But what was interesting is then I kept going. So there's up to 5. And I said, what if we allow 6? Now I did 6 and 6 times 2, which is 12. I didn't include 18 because that goes beyond 15. And we're just asking about what gets to 15. So then I did 7 and 14, 1 7 and 2 7s. And then I did 8. I didn't do 2 times 8 because that would be 16. I did 9. I didn't do 2 times 9 because that would be 18. And then the only interesting thing, and I think I did this right, was this number. And the reason I put a 16 there is because, and maybe I did this wrong, because there are 4 10s, and there's 4 jacks, and there's 4 queens, and there's 4 kings. So whichever 10 you use, there are 16 total ways you can pick a 10 out of the deck. So I did that, and I got this number. And that was this unsatisfying thing, was because I don't match the final answer this person had. Everything was going smoothly, but I'm about 300 more than them. So I'm wondering if I'm overcounting something. As I've said, I've matched everything so far. I just need to keep going. So maybe in a future video when I have more time, I'll check the 6s, I'll check the 7s, and maybe at some moment they will differ, in which case I'll find out, did they forget something? Or did I make a mistake in my setup? But I'm going to leave that for now. If my answer is right, it's the only place I found it published online. I am sure someone's done this before, but let's pretend that it's something I've proven for the first time. I think it's much more likely that I have an error somewhere because I'm not matching this other answer. But I just find that kind of the surprising use of polynomials to count using their coefficients and exponents. I hope you find that interesting as well.